Okay, in this video we're going to be looking at the measure of variation. Now, this video we're going to be talking about how to find the standard deviation, the variance, and the range of a set of data. Now, in the last video that I discussed, we talked about the measures of center. So now we're going to be looking at variation and how the data values vary or how they're spread. Okay. Now, there are three types of measures of variation. One of them is the range. Now, this one is going to be the easiest one that we're going to be able to find, because the range, by definition, is nothing but this. It is the difference. It's the difference between the maximum data value and the minimum data value. Okay. So that's the definition of what a range is. You're taking the difference between the maximum data value and the minimum data value. So, in other words, the formula for just simply finding the range is the maximum data value, and I'll just say maximum, or the highest data value minus the minimum data value, or we can just say the lowest data value in that set of data. Okay, and that'll just give us what the range is. Okay, and we'll look at some examples shortly. But I just want to introduce the measures of variation to you. There are three of them. So I've already introduced the first one, which is the range. Now the second one is the standard deviation of a set of data. And the standard deviation is going to be denoted by a lowercase s. And by the way, that represents a sample standard deviation. So this is a standard deviation of a sample. That's the notation for a sample standard deviation. And by definition, it is this. It is a measure of how much those data values deviate from the mean. Okay? In other words, it gives us the spread of that data, how much those data values are spread out from the mean, or from the sample mean. And there is a formula for the sample standard deviation. Now, we're going to look at two formulas. One of them is this. S is equal to the square root of the summation of x minus x bar, and that quantity squared, divided by n minus 1. And all of this is underneath the square root symbol. So this is the formula for finding the sample standard deviation. Now, what this means is this. You have to take each individual x value, subtract it from the mean. But first you have to find out what the mean is first, and then subtract your individual data value from the mean, and then square it, and then you'll take the sum of the square of that and then divide that by n minus 1. However, we do have what we call a shortcut formula, which I'll be using in this particular video when I do the examples here. So here, this is going to be s is equal to the square root of n, which is the number of data values that you have, multiplied by the summation of your x squares. What you'll do is you'll square your x's and then take the sum, minus the sum of all your x's, and whatever that sum is, you're going to turn around and square it. So you'll first take the sum of all your x's and then square it. And then all that's divided by n times n minus 1. We call this the shortcut formula. The reason for that is that you're only going to be using your x values and the square of your x values in this particular formula. Okay. That's why it's called the shortcut formula for your sample standard deviation. And this is the one that we will be using in this video when we do examples that require us to find the standard deviation of a set of data. Okay. Now there are some properties of the standard deviation, by the way, that I'm going to put up here. Now the standard deviation is nothing but the measure of how data values deviate from the mean, or how those data values are spread from the mean. The value of the standard deviation is usually positive, and is zero only when all the data values are the same number. So if all your data values are exactly the same, then that means the standard deviation is automatically going to be zero. There is no deviation from the mean. And also, your standard deviation will never be negative. Okay? Also, larger values of S indicate greater amounts of variation. So, if your standard deviation is large, then that means that the variation is greater. And then you have the value of the standard deviation. It can increase dramatically when you include one or more outliers. And outliers, by the way, are those data values that are very far away from the others in that set of data. Okay. So those are just some properties of a standard deviation. Now the third is the variance. Excuse me. The third measure of variation is the variance. And what the variance is this. If you already know what the standard deviation is, you can easily find the variance, because that is simply just the square of the standard deviation. It's the square of the standard deviation. So in this case here, the variance would just simply be S squared. S is the standard deviation. The variance, you just take the square of that standard deviation in order to get its variance. Okay. Okay, now there are some notations that you do need to know throughout this particular course that deal with variance and standard deviation. Now I'll just mention those. Your lowercase s is always your sample standard deviation. We already talked about that. And S squared, of course, that's your variance. Now you're also going to see for a population the Greek letter sigma. Okay, this is the Greek letter sigma, lowercase sigma, by the way. That represents the population standard deviation. And sigma squared is the population variance. That represents the square of your population standard deviation. Okay, so that's some of the notation that you're going to be seeing throughout this course, especially these last two. Sigma is the population standard deviation, and sigma squared is your population variance. Now for a sample, lowercase s is your sample standard deviation, s squared will be your variance. Okay, now let's take a look at some examples of how to find the range, the standard deviation, and the variance of a set of data. Okay. All right, now let's take a look at this example here. You have 6 different second-year medical students at Bellevue Hospital measuring the blood pressure of the same person. The systolic readings in milligrams per Hg are listed below. Find the range, variance, and standard deviation for the given sample data. And if the subject's blood pressure remains constant at the medical students and the medical students correctly applied the same measurement technique, what should the value of the standard deviation be? Okay, and these are the data values that we have: 150, 139, 130, 133, 127, and 146. Okay, so here we're finding the range of this set of data. Let's start with that. Anytime you find the range, you're taking the maximum data value and you're going to subtract the smallest data value from it. Here, the maximum data value in this set of data is 150, minus the smallest data value in this set is 127. So if we do 150 minus 127, we're going to end up with 23. So the range of that set of data would simply be 23. Okay, now next we need to find the sample standard deviation. Sample variance. Let's start with that. Okay. Now, for the sample variance, we're going to use the shortcut formula because this is going to be much easier to use. And here's how we set this up. We're going to have 2 columns. One will be x and the other one will be x squared. Your x's are going to be your data values. Now, you don't necessarily have to put this in numerical order, so we can write down those data values for x as is. 150, 139, 130, 133, 127, 146. And I'm going to put here the sum of my x's. Okay, now I'm going to go ahead and add up these data values here for x, because that's going to represent the sum of all my x's here. So if I add 150, 139, 130, 133, 127, and 146, you'll get a total of 825. So the sum of those data values will be 825. Now for my x squares, I'm going to square each individual x value one at a time. So if I do 150 and I square it, that's like 150 times 150, you're going to get 22,500. Then for 139, and you squared will be 19,321. And then for 130, you're going to get 16,900. That's 130 squared. 133 squared will be 17,689. 127, and if you square that, that's going to be 16,129. And then 146, and if you square that, that's going to be 21,316. Now I'm going to take the sum of the x squares. That's this column right here. That's the summation of your x squares. Okay? So if I add 22,500 to 19,321 to 16,900 to 17,689 to 16,129 to 21,316, I'm going to end up with 113,855. that represents the sum of all your x squares. Okay? Now, I'm going to use all of this in my shortcut formula. And by the way, the n, there's 6 data values, so n is equal to 6. So my sample variance, which is s squared, is going to be this. I'll rewrite the formula as n times the summation of x squared minus the square of the sum of all your x's. All that's divided by n times n minus 1. So now with your s squared, n is 6, so that's going to be 6 times the summation of your x squared. That's this number right here, 113,855. Minus the summation of your x's. Here, the summation of all your x's, that's 825. And that's going to be squared. All that's divided by n times, well, n is going to be 6 times n minus 1, or 6 minus 1. Now, we can simplify the numerator and the denominator separately. So in this case here, if I do 6 times 113,855 minus 825, and then you square it by hitting your x squared button on your calculator, the numerator will be 2,505. And that's divided by, now the denominator, if I do 6 minus 1, that's going to be 5. 5 times the 6 on the outside will be 30. Okay, so I'm just applying the order of operations by doing what's inside the parentheses first. So if I do 2,505 divided by 30, that will give me 83.5. So my sample variance would simply be 83.5. That's the sample variance. Now for the sample standard deviation, which is the other part that I'm going to need to do, well, I know what the variance is. So if I do the sample standard deviation, I just need the square root of the variance. So here s is the square root of s squared. Okay? So now my sample variance was 83.5, so to get the sample standard deviation, you just take the square root of 83.5. And to one decimal place, this will end up being 9.1. So the sample standard deviation for this set of data would simply be 9.1. And that's how you find the range, the variance, and the standard deviation of a sample data set. Okay, I'll do another problem. Now this one has negative signs in it. Listed below are the arrival delay times in minutes of randomly selected airplane flights from one airport to another. Negative values correspond to flights that arrived early before the scheduled arrival time, and positive values represent lengths of delays. Find the range, variance, and standard deviation for the set of data. Some of the samples are negative, but can the standard deviation ever be negative? Okay. And these are the data values that we have: negative 13, negative 21, negative 7, 11, negative 33, 11, and negative 4. Alright, so in this case here we want to find out what the range is. The highest data value in this set is 11. And the smallest is negative 33. So we're subtracting the smallest from the largest, so this will be 11 minus negative 33. Now, 11 minus a negative 33 is the same as saying 11 plus 33, which will be 44. So the range of that set of data will simply be 44. Okay. Now next we want the sample variance. Okay. Alright, now for the sample variance, first of all, there are 7 data values, so we'll let n equal to 7. Okay, now, the first column is my x, the second column is x squared. Okay, and then I'm going to list all my data values in the x column. So here I have negative 13, negative 21, negative 7, 11, negative 33, 11, and 4. And I'll go ahead and take the sum of all the x's. Okay, now, when you add negatives, make sure that you use the negative key, which is at the very bottom of your calculator. Okay, that's right next to the decimal point. That has a little minus sign with the in the parentheses here. That's your negative key. Make sure you use that to add those numbers. So in this case, if I do negative 13, negative 21, negative 7, 11, negative 33, 11, and 4. I'm sorry, negative 4. Okay, so I need to go back and correct that. That will give me negative 56. So the sum of all your x's will be negative 56. Now for the x squares, you're going to square each individual x value. So when we square negative 13, that's like negative 13 times negative 13. You're squaring a negative, so that's going to be a positive. And in this case, negative 13 and u squared will be positive 169. And if you want to do this on the calculator, you can. But make sure you use parentheses around the negative 13. And then square it on the outside, because you have to close the parentheses and then square it to get the actual number of 169. If you leave the parentheses off, you're going to get a wrong answer. And the reason for that is this: it takes that 13 and squared and then puts the negative sign last. So you want to do it this way. Want the negative 13 inside the parentheses and the exponent of 2 on the outside, for it to be a positive value. And the same thing for negative 21, that's squared, that's going to give you a positive 441. And then negative 7 and u squared will be positive 49. 11 squared will be 121. Negative 33 and u squared will be a positive 1089. 11 squared will be 121. Negative 4 and u squared will be a positive 16. So we'll go ahead and take the sum of these individual x squared values here. Okay, so if you add those up, you'll get 2006. And that represents the sum of your x squares. Okay, now we have what we need to find the sample variance, which is this x squared formula equaling to n times the summation of x and u squared, or the summation of x squared minus the sum of all your x and then you square that. All that's divided by n times n minus 1. And then we just substitute those values into that formula. So for s squared, n is 7, so there'll be 7 times the summation of x squared. That's this number right here, 2006. minus the summation of x, that's negative 56, and that's going to be squared. All that's divided by n is 7, so it'll be 7 times 7 minus 1. Okay, now using our calculator, we got 7 times 2006 minus, and in parentheses, negative 56, close parentheses, and hit your x squared button to square it. So the numerator will be 10,906. And then the denominator is this. 7 minus 1 will be 6. 6 times 7 will be 42. So now you get 10,906 divided by 42, which means your s squared would be, to one decimal place, that would be 259.7. So the standard deviation for this set of data will be 259.7. I mean the sample variance. That's the sample variance. Now for the sample standard deviation, we just simply take the square root of our variance. So s is simply the square root of your variance, which is s squared, and s squared we found that out to be 259.7, so the square root of 259.7, that's 16.1, rounded to one decimal place. So the sample standard deviation there will be 16.1. Now notice that some of the sample values are negative, but can the standard deviation ever be negative? And the answer to that is no, because we already talked about the fact that the standard deviation will never be negative. Okay? And that reason is because you're squaring these negative numbers. Anytime you square negative, you're going to get a positive values. Okay? And I think I need to go back to the other example that I did was if these data values were exactly the same all the way through, that standard deviation will end up being 0 because there's no variance in those data values if they're all the same. Okay? Alright, so this is pretty much how you'll calculate the range and the sample variance and the sample standard deviation of a set of data. Okay, now let's look at some other things that are related in this particular section. And the one that I want to talk about is the range rule of thumb. Okay. So here the range rule of thumb is this. Now it's based on the principle that for many data sets, the vast majority or 95% of the sample values lie within 2 standard deviations of the mean. Okay, that's basically what that range rule of thumb is, where you have at 95% of your sample values are within 2 standard deviations of the mean. And we do have a minimum usual value and a maximum usual value. So the minimum usual value is this. You take the mean, you'll subtract from it 2 times the number of standard deviations. Or 2 times the standard deviation. You'll subtract that from the mean. And the maximum usual value is going to be the mean, but it'll be plus 2 times the standard deviation. Okay. So here we use these two formulas to find the minimum usual and the maximum usual value of a set of data. And here's one example of just that. Okay. Let's say we had a certain group of subjects. They had pulse rates with a mean of 73.4 beats per minute and a standard deviation of 11.1 beats per minute. Would it be unusual for one of the test subjects to have a pulse rate of 75.6 beats per minute? Okay, so now this is where we use that particular formula for the minimum usual and the maximum usual values. And if that number of 75.6 falls within that range, then that means that data value is usual. If it's outside, it's unusual. So in this case here, the minimum usual value is always the mean minus 2 times the standard deviation. And in this case, we're told that the mean was 73.4 beats per minute minus the standard deviation of 11.1, so that would be 2 times 11.1. Well, 2 times 11.1 will be 22.2, and 22.2 from 73.4 would be 51.2. So the minimum usual value will be 51.2. Okay, now for the maximum usual value. Now, your maximum usual value, of course, is the mean plus 2 times the standard deviation. Again, the mean was 73.4. This time it's going to be plus 2 times 11.1, which was our standard deviation. And 2 times 11.1 was 22.2. So 73.4 plus 22.2 will give me 95.6. So the maximum usual value will be 95.6. So using these two values, my range is going to be this. From 51.2 to 95.6 beats per minute. So in this case, that's going to be the range of usual pulse rates. Okay, so, and in this problem, we were dealing with 75.6 beats per minute. Here, 75.6 lies between 51.2 and 95.6. So that is a usual value. Okay, So we will say here, now they ask, would it be unusual for one of the test subjects to have a pulse rate of 75.6 beats per minute? So here, this will be, no, it would not be unusual. And the reason for that, because that data value lies within those two, that range of 51.2 and 95.6. Now, had it lied on the outside, then it would be unusual. Okay. Okay, the next thing I want to talk about is the empirical rule for data that has a bell-shaped distribution, or what they call a normal distribution. Okay. So the next thing we'll look at is the empirical rule. Which is usually 68, 95, 99.7% rule for a bell-shaped distribution. Okay, now what that rule states is this. And it will be best for me if I draw a normal curve that looks like this. And I want you to know this is not the best normal curve. Okay. Okay. Now let's say that the mean is at the center of this normal curve. So here, the center right here is your x bar. That's your mean. Okay. And then we have standard deviations here. So if I go one standard deviation to the right, it'll be x bar plus s. Go another one, it'll be x bar plus 2s. And then go out another one, it'll be x bar plus 3s. Okay. So each one of these represent one standard deviation past the mean. And if I go to the left, this will be x minus s. If I go another standard deviation to the left, it'll be x bar minus 2x. And then another one will be x bar minus 3s. Okay. Now, what the empirical rule states with this particular normal curve. Within one standard deviation of the mean, that means one standard deviation to the left and one standard deviation to the right, that's this area right here, 68% of those data values will lie within one standard deviation of the mean. 68% of those data values will lie within one standard deviation of the mean. Now, if I go out two standard deviations to the left and to the right, so here's two standard deviations to the left and two standard deviations to the right, that's this area here. According to the empirical rule, 95% of those data values will lie within two standard deviations of the mean. And then finally, if I go three standard deviations of the mean, 3 to the left and 3 to the right, that's going to be all of this here. Then according to the empirical rule, 99.7% of the data values will lie within 3 standard deviations of the mean. Okay? So this is basically what that empirical rule is stating in regard to the normal curve or the bell-shaped distribution. Okay. Now let's look at some examples that are related to, well, let's look at one example that's related to the empirical rule. Like this one. Heights of men on a baseball team have a bell-shaped distribution with a mean of 186 and a standard deviation of 6 centimeters. Using the empirical rule, what is the approximate percentage of men between the following values? And in part A, it says between 174 centimeters and 198 centimeters. Part B is 168 centimeters and 204 centimeters. Okay, so let's draw a normal curve. It looks like this. And then, now the mean is in the center, so the mean here is 186. And then we're going to go 3 standard deviations out. Now my standard deviation was 6. That was given to me in the problem. So if I go 1 standard deviation past the mean of 186, that number will be 192. Okay? And then I'm going to keep adding 6 each time. So if I add another 6 to this 192, that'll be 198. That represents 2 standard deviations to the right of the mean. Add another 6 to the 198, you'll get 204. That's 3 standard deviations to the right of the mean. Okay, and then we're going to go 3 to the left of the mean. Well, 1 standard deviation to the left, you'll subtract 6 from 186, you'll get 180. For 2 standard deviations of the mean, let's do 180 minus 6. That's 174. And let's do 174 minus 6, that'll give you 168, which represents 3 standard deviations of the mean. Okay, so that's going to help us answer part A. The approximate percentage of men between 174 and 198. Here's 174, and here's 198. If you take a look at this, those numbers are within 2 standard deviations of the mean. And according to the empirical rule, 95% of those data values lie within 2 standard deviations of the mean. So 174 to 198 represent 95% of the men between those values. That's part A. Part B, 168 and 204. Well, here's 168 over here, and 204 is over here. Those values are within 3 standard deviations of the mean. And according to the empirical rule, 99.7% of the data values are within 3 standard deviations of the mean. So between 168 and 204 centimeters, 99% of the men have heights between 168 and 204. Okay, so that's how we apply the empirical rule to do these types of problems. Okay, and the last thing I want to talk about is Cassidyshevs Theorem, which is applicable to any distribution. Now, if you recall, the empirical rule is only applicable to the normal distribution. But with Cassidyshevs Theorem, here's how we spell Cassidyshevs Theorem. Okay, this applies to any data set, regardless of whether it's normal. But with the empirical rule, it's only applicable to the normal distribution. Cassidyshevs theorem is applicable to any data set. Okay? So according to Cassidyshevs theorem, is this. At least 75% or 3/4 of all values are within 2 standard deviations of the mean. Okay, at least 75% or 3/4 of all your data values are going to be within 2 standard deviations of the mean. And at least 89%, or we can say 8/9 of all data values, of all values, I'll say, are within are within 3 standard deviations of the mean. Okay, so that's what Cassidyshevs Theorem is. Okay. And here they use that formula 1 minus 1 over k squared. Okay. Now that's the proportion or fraction of any set of data lying within k standard deviations of the mean. And that's always at least 1 minus 1 over k squared. K is a positive number greater than 1. Okay. So this is where k is going to be greater than 1. And k represents the number of standard deviations. Okay. And we were using these for k is equal to 2 and for k is equal to 3. So this came from k is equal to 2. This one came from k is equal to 3. Okay. So here is that one example where we apply Cassidyshevs Theorem to a situation like this. Now here we're dealing with heights of women having a bell-shaped distribution with a mean of 159 centimeters and a standard deviation of 7. Using Cassidyshevs Theorem, what do we know about the percentage of women with heights that are 3 standard deviations of the mean? What are the minimum and maximum heights that are within 3 standard deviations of the mean? Okay. Now, we can use that formula 1 minus 1 over k squared. Okay. Now here we can use k is equal to 3. Now, we already know within 3 standard deviations of the mean from what I just mentioned. Okay. Now, from what I just mentioned, that 89% of all values are within 3 standard deviations of the mean. So here, we're dealing with 3 standard deviations of the mean, so that means that, in this case, 89%, or at least 89%. Okay, so let me erase this. At least 89% of women, they have heights within 3 standard deviations of the mean. Okay. And of course that mean is 159, so within 3 standard deviations of the mean, at least 89% of those women have heights within 3 standard deviations. But now we want the minimum and the maximum heights that are within 3 standard deviations of the mean. Okay, so now let's find the minimum height. And that's going to be the mean minus 3 times the standard deviation. And in this case, your mean was 159 that was given to us in the problem, minus 3 times, the standard deviation was 7. So this will be 159 minus 21, which will be 138. So the minimum height would be 138 centimeters. Now for the maximum height, of course, will be the mean minus 3 times your standard deviation. And here your mean, again, that's 159. This time it's going to be plus. I should have said plus here. Okay? So it'll be 159 plus 3 times 7. Because 7 was your standard deviation. So now you got 159 plus 21 from the 3 times 7. So 159 plus 21 would be 180. So your maximum height would be 180 centimeters. So here, the minimum and the maximum heights that are within 3 standard deviations of the mean would be from 138 centimeters to 180 centimeters. Okay? So that's how you find your maximum and your minimum height in this particular problem, using Cassidyshevs Theorem. Alright, so this will conclude this video on the measures of variation.